In the last lecture, we started investigating the behavior of plane wave at media interface. Matching the phase for the incident and the other waves which are reflected and transmitted wave at the media interface, we got the laws of reflection and laws of refraction. Now, following that, today we will investigate how much energy is transferred to the second medium and how much energy is reflected from the dielectric interface. So, today essentially we discuss the problem of reflection and refraction at the dielectric interface. As we took in the previous lecture, we are still considering the media which are lossless media, that means the conductivity for both the media is 0, but the two media can have different permeability and different permittivity. So, in that situation we are asking a question, how much power gets transferred from one medium to another and how much power is reflected from the media interface. As we discussed, the problem essentially now is that you have a media interface, you are having different medium properties on the either side of this interface, and then we are interested in now finding out two quantities. One is what is called the reflection coefficient, which we define as the amplitude of the reflected wave to the amplitude of the incident wave, and the transmission coefficient, which is the ratio of the amplitude of the electric field or the transmitted wave to the electric field for the incident wave. These quantities we have defined for the electric field, and as we know, since the wave nature still remains the plane wave nature, as and when required we can always find out the magnetic fields for all the three waves, the incident, reflected and the transmitted wave. So, now the analysis is very straightforward. Essentially we write down the electric fields and the magnetic fields in the two media for the three waves, and then you apply the boundary conditions at the interface for the electric and magnetic fields, and then by doing some algebra essentially you get this quantity which is ER by EI, which is the reflection coefficient, and ET by EI, which is the transmission coefficient. However, as we mentioned earlier, that when we are interested now in these quantities, the electric field is a vector quantity. So, when the wave is incident on the dielectric interface, the electric field vector in general can make an angle, arbitrary angle, with respect to the plane of incidence. So, if you solve this general problem, that when the wave vector is making an arbitrary angle with respect to the plane of incidence, the problem is rather complicated. So, what we do generally, we split this problem into two. So, essentially we take the two components of the electric field vector, one is perpendicular to the plane of incidence and other one is in the plane of incidence, and then we have two cases for which we can find out the reflection and transmission coefficients, and if we get these quantities for these two cases, then we can always combine the two to find the any arbitrary direction for the electric field. So, the problem of reflection and refraction at dielectric interface is decomposed into two. One is when the electric field is perpendicular to the plane of incidence, and we call that as the perpendicular polarization. So, essentially what we are doing now is whatever is the polarization of the incident wave, as we have seen, this polarization can be decomposed into two orthogonal linear polarizations. So, we are decomposing this into two linearly polarized waves, one which is polarized perpendicular to the plane of incidence, other one which is polarized in the plane of incidence, and then we find out the reflection and transmission coefficient for these two cases. So, let us first investigate that the reflection and refraction coefficient for a perpendicular polarization. So, as we have taken earlier, let us say this is the interface, and as we took this direction is the x direction, let us say this is the origin, this is the z direction, the y direction is coming out of the plane of the paper, so this is y direction, Again, let me remind you, we are choosing this direction such that the right handed coordinate system, that rule is satisfied. Now, let us say the wave is incident on this. So, this is the direction of the wave vector, which is making an angle, let us say theta I, with the normal to the dielectric interface, and this wave vector is lying in the plane of the paper. That means the plane of the paper itself is plane of incidence. And the polarization for this wave is perpendicular polarization. So, either the electric field might be coming out of the plane of the paper, or it might be going inwards from the plane of the paper. So, let us say, without losing generality, let us say the electric field is coming out of the plane of the paper. So, this is the incident electric field, which is now oriented in y direction. Then let us say this is the transmitted wave, which makes an angle theta t, and there is a reflected wave which will make an angle same as the incidence angle, which is theta I. So, this is the reflected wave. Now, one can argue that since we have to satisfy the boundary conditions at the interface, and one of the boundary conditions we can satisfy is the tangential component of the electric field should be continuous across the boundary. If this field is y oriented, then both these fields also must be y oriented, not necessarily in positive y direction, it could be positive or negative, but it is oriented in the y direction. And the reason is very simple, that if I have to satisfy the boundary condition, then sum of these two electric field which are tangential to the interface, this should be equal to the electric field which is for the transmitted wave. If I have field for this transmitted or reflected wave which is not perpendicularly polarized, if it is lying, if it is having some component in the plane of incidence, then the two components which are lying in plane of incidence will satisfy the boundary conditions, but it will not have any role to play with the incidence electric field. What that means is that you might imagine a situation there where there are two electric fields which are for this wave and this wave, but these are not because of the field which is incident on the boundary. So, as far as the effect of this incidence wave is concerned, the electric field must lie perpendicular to the plane of incidence so that the boundary condition is satisfied. So, then without losing generality, we can assume that all the three electric fields are y oriented, that means they are oriented in positive y direction. If our convention was wrong, then we will get negative sign for the electric field for transmitted and refracted wave, that means the wave will be going inwards in the plane of the paper. So, without losing generality, we can say this also is positive y oriented. So, this is Et, and this is also positive y oriented. So, let us say this is Er. So, all the three electric fields now coming out of the plane of the paper. Now, we have to write down the magnetic fields, and for writing the magnetic field essentially we use the Poynting vector argument, and that is we must choose the direction of the magnetic field such that the Poynting vector must be in the direction of the wave propagation, that means it must be along the wave vector. So, in this case, since the electric field is coming outwards, if my fingers go from electric field to magnetic field, thumb must point in the direction of the wave propagation, and E and H must be perpendicular to each other. So, it is very clear, since E are for all the three waves are coming perpendicular to the plane of the paper, the magnetic field vectors for all the three waves must lie in the plane of the paper, that is they must lie in the plane of incidence. So, they are perpendicular, they lie in the plane of incidence, whether they would lie this way or this way, that will be decided by the Poynting vector. So, in this case, since the E is coming outwards, my finger should go like this, so that thumb gives me the direction of the power. So, this must be the direction of the magnetic field. So, this is the Hi, so that I get E cross H which will be the direction of the pointing vector. Same thing I can do then for here, that this also should give me h in such a way that pointing vector in this direction. So again you will get this is the direction which is ht. In this case, however, since the wave is now going in this direction and electric field is coming outwards, the magnetic field should be in this direction, so that E cross H gives me the power which is in this direction. So I get for this wave the magnetic field will be oriented in this direction. So what we do, first we assume the direction for the electric fields, then by using the pointing vector arguments we write down the directions for the magnetic fields in the vector form, and also we know since these waves are transverse electromagnetic waves, the ratio for this is given by the intrinsic impedance of the medium. So as we saw here, we have EI upon HI, that is equal to eta 1, which is the intrinsic impedance of the medium 1, ER upon HR, that is also equal to eta 1, which is the intrinsic impedance of this medium 1, and here ET upon HT, that is equal to eta 2, which is the intrinsic impedance of medium 2. So as we have seen, if the medium parameters are mu 1 epsilon 1 for medium 1, and for this side it is mu 2 epsilon 2, then we have this eta 1, which is intrinsic impedance of the medium, which is square root of mu 1 upon epsilon 1, and eta 2 for this medium, which is equal to square root of mu 2 upon epsilon 2. So once I know the medium parameters, I can find out the intrinsic impedance. Once I know the intrinsic impedance, I know the magnetic field from this relation. Now essentially we decompose the magnetic field into two, and then we can apply the boundary conditions appropriately. Electric field, note, inherently parallel to the interface, that means it is tangential to the interface at this location, so we can satisfy the boundary conditions. So first thing is we write the functional form for this electric and magnetic fields, including the phase function. Then we apply the boundary condition that tangential or normal component of electric or magnetic field should be continuous across the boundary. So if this angle is theta I, I can decompose into two components. So one is this component, one is this component, and this will be equal to, this angle is theta I, so this angle also will be theta I. This angle will be theta I. If I resolve this again in two components, that this angle will be theta t. So this component, which is tangential component of our magnetic field, will be HR into cos theta I. This will be HR into sin theta I, and same is true for the other three waves. Let us now first write explicitly the expression for the electric fields. So if I, let us say I take the incident wave, the electric field EI is having some magnitude EI, and it has a phase function which is e to the power minus j beta 1 into, as we saw last time when we wrote the phase function, this will be equal to x times sin of theta I plus z times cos of theta I. So this will be x sin theta I plus z cos theta I. for the reflected wave we have ER, that is the amplitude ER, e to the power minus j beta 1 x sin theta I. But now this wave is now going in the opposite direction with respect to z. So, either I can find out the direction cosine, which is this angle with respect to z axis was theta I, but for this wave the angle is actually pi minus theta I. So, it will be direction cosine of pi minus theta I corresponding to that. So, that will be minus z cos of theta I, and then we have a transmitted wave which is E t equal to sub magnitude E t e to the power minus j beta 2 x sin theta t plus z cos theta t. And all these waves are fields are y oriented. So, I can put, if you want, a unit vector for all this which is y oriented. Now, if they have to satisfy the boundary condition, and since these all three fields are continuous and tangential to this boundary, the EI plus ER should be equal to ET at the dielectric interface, which is z equal to 0. So, this plane, which is the dielectric boundary, is defined by z equal to 0 because we have taken the origin at the interface. So, at z equal to 0, these sum of these two fields should be equal to the transmitted field. So, essentially I have from the boundary condition that tangential component of E should be continuous. We will get from here EI plus ER is equal to ET. So, if I substitute, I will get the three phase functions, this quantity which will be this total function plus this quantity plus this at z equal to 0. So, I get from here EI e to the power minus j beta 1 x sin theta I plus ER e to the power minus j beta 1 x sin theta I, that is equal to E t e to the power minus j beta 2 x sin theta t. So, this is the boundary condition at z equal to 0. Now, we have already established the Snell's law, which says beta 1 sin theta I is equal to this quantity is same beta 1 sin theta I, and that is equal to beta 2 sin theta t. So, from the Snell's law we have beta 1 sin theta I is equal to beta 2 sin theta t. That means this phase function is same for all the three waves. Okay. So, essentially this term is a common term because the Snell's law satisfies that this quantity is equal to this quantity. So, what that gives you is that EI plus ER, that is equal to ET. And that you will see this phase matching condition essentially is true for all the components, whether you have normal component or a perpendicular component, or normal component or tangential component. This phase term is same. So, what will happen is that the component which you take for electric or magnetic field, that will be either this quantity multiplied by cos theta I or sin theta I, depending upon whether we take tangential component or normal component, but the phase function is same for all the components, which is given by this. So whatever boundary condition we satisfy, this phase function will always be same for the incident and the transmitted wave. So what that means then the boundary conditions have to be applied only on the amplitude term, which is the amplitude of the incident, reflected and the transmitted wave. So we have one relation between these, and that is equation 1, which we can use later on for finding out the quantities, as we mentioned, the reflection and transmission coefficient. The second boundary condition which we get either from the continuity of the normal component of the magnetic field, or in this case, since we are talking about dielectric media, there are no surface currents. So we can always also use the continuity of the tangential component of magnetic field. So as we have seen earlier when we talked about boundary conditions, the tangential component of magnetic field cannot be applied if there is a possibility of surface current. However, as we have seen, the surface currents are for ideal conductors. So if you have a dielectric boundary like this, there is no surface currents, and then even the tangential component of magnetic field can be applied. So we have tangential component of magnetic field, which is Hi cos theta I, that is the tangential component. So this is Hi cos of theta I. This component is Hr cos of theta I, and this component, tangential component, this one is Ht cos of theta t. So we can apply the continuity that this minus this, because they are in opposite direction, that should be equal to the tangential component, which is Ht cos theta t. So we can apply the, since there are no surface current, even tangential component of H is continuous at the boundary. So from here we get Hi cos theta I minus Hr cos theta I, that is equal to Ht cos theta t. So from here this term minus this term, that is equal to this term. And we now know the relation between E and H. So I can substitute for H, which is Ei upon eta 1, Hr is Er upon eta 1, and Ht is Et upon eta 2. So this thing I can write as Ei upon eta 1 cos theta I minus Er upon eta 1 cos theta I, that is equal to Et upon eta 2 cos theta t. That is your second equation, which relates the electric field components across the boundary. Now remember, we are interested in now finding out two quantities. One is the reflection coefficient, which is Er upon Ei, another one is transmission coefficient. So using these two equations, I can now find out these two quantities. I have one equation which is this, the other equation which is this, and then by just simple algebraic manipulation I can find out the reflection and transmission coefficient for this wave, and that will be, so I get now reflection coefficient, and as we saw, this is denoted by gamma. But now in this case we are having a polarization which is perpendicular polarization. So we call this is the reflection coefficient gamma perpendicular, and that will be equal to, just if you solve these two equations, we get eta 2 cos theta I minus eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t, and the transmission coefficient tau, and again we put this suffix perpendicular for perpendicularly polarized wave, that is equal to 2 times eta 2 cos of theta I, that divided by eta 2 cos of theta I plus eta 1 cos of theta 2. We can verify that from this equation 1, if I divide this equation by EI, I will get 1 plus ER upon EI is equal to ET upon EI. So, that will give me 1 plus gamma is equal to tau. So, we can verify that it will satisfy the condition 1 plus gamma is equal to tau. So, this is perpendicular. So, just after the boundary, if I find out what are the fields, the electric field, then the reflection coefficient gives me just beyond the boundary what will be the value of the transmitted field, and just this side of the boundary, left side of the boundary in medium 1, what will be the amplitude of the electric field. And once we get these quantities ER and ET, then of course we have this phase function, so we can find out the wave at any location, any point in space in medium 1 and in medium 2. So, in medium 1 essentially we have superposition of the wave which is 1, which is incident, and the wave which is reflected from the boundary. So, at any point in space you have to find superposition of these two, whereas if you go to the medium 2, then we have only this wave. So, we can find out the wave at any location in medium 2. Few things can be noted from this expression for reflection and transmission coefficient. One is the reflection coefficient is always less than or equal to 1. So, this quantity means mod gamma, if you take mod of that, magnitude of this quantity, less than or equal to 1. Whereas this quantity, which is the transmission coefficient, it could be less than 1, it could be greater than 1. Now, if you recall, this quantity here, the gamma is the reflection coefficient, and the Poynting vector is proportional to mod E square. So, if gamma is less than 1, that means the Poynting vector magnitude for the reflected wave is always less than 1. That is very straightforward. So, what essentially we are saying is, if there is some wave which was coming to the media, then it had got some power density along with it. When the wave got reflected, the power density in this wave is always going to be smaller than the power density coming from this wave. So, the reflection coefficient is always less than 1 is quite obvious. What is the meaning of then the transmission coefficient is greater than 1? Because there may be situation here when this quantity eta 2 cos theta I is greater than eta 1 cos theta 2, that time the amplitude of this would be greater than 1. That means the electric field in medium 2 would be larger compared to the incident electric field. Does that then mean that the Poynting vector in that for that transmitted wave is greater than Poynting vector of this? The answer is no. Why? Because although the electric field is larger here, the intrinsic impedance which is related to this quantity epsilon 1 and mu 1, the magnetic field will reduce in a proportion, so that this Poynting vector for this will be always less than the Poynting vector of this. After all, there has to be conservation of the power. So, if you got certain power density coming from here, the power density which are going for this wave and this wave, they must be, some of these two must be equal to the power which was carried by the incident wave. So, though the electric field could be larger in the second medium, the Poynting vector for both the waves, the reflected and transmitted, will always be less than the Poynting vector of the incident wave. When the wave is reflected from the boundary, that time there may be a phase reversal for the wave, or there may not be a phase reversal from the wave. This quantity is always positive. So, when the wave is incident on the dielectric medium, the transmitted wave is always in the phase with the incident wave, but the reflected wave can be in phase, can be out of phase, 180 degree out of phase. That means the electric field, if it is like this for the incident wave, the electric field for the transmitted wave will be always coming out of the plane, this if this was coming out of the plane, whereas for the reflected wave it might come out of the plane or it might go inside the plane. Both possibilities might exist depending upon the angle of incidence and the medium parameters. So, these are some broad conclusions one can draw for this wave which is perpendicularly polarized wave. The next case, which is the parallel polarization, the analysis of this wave is identical to this. That means you again write down the wave vectors, you write down the fields, again you match the boundary conditions, and then you get the expression for the reflection and transmission coefficient. So, very quickly we can get what is called the parallel polarization. That means in this case now the electric field is lying in the plane of incidence. So, this, say this direction is x, this is z, this is y, and again the wave is incident at an angle which is theta I, it is reflected an angle which is theta I, this is theta t, and now the electric field is lying in plane of incidence. That means it is lying in this plane of the paper. So, if the electric field lies in the plane of paper, the magnetic field must lie perpendicular to the plane of the paper, because these two must be perpendicular to each other. So, in this case, without losing generality, what we assume is that all the magnetic field vectors are y oriented, they are coming out of the plane of the paper, and then appropriately choose the electric field's direction so that you get the correct Poynting vectors. So, let us say the magnetic field for this was coming out, this is given by Hi, this is Ht, and this is Hr, and I must get the electric field so that the Poynting vector in this direction. So, since H is like this, your E must be going this way. So, E cross H gives me the correct Poynting vector. So, I get this is the direction for my EI, this is the direction for ET, and for this wave which is going in opposite direction, again I must get E cross H which is this way. So, E will be pointing this way. So, this is my ER. Again I can take the component of these vectors, tangential component. The magnetic field now is tangential to the interface. So, this is, if this angle is theta I, again this is theta I, this is theta I, this is theta t. So, this component is Et cos theta t. This component is EI cos theta I, and this is ER cos theta, this component. So, again by matching the boundary conditions, essentially we can get now, since the magnetic field is fully tangential, and recalling that the phase function for all of them is same as we saw in the previous case, we get now two conditions, Hi plus Hr is equal to Ht, and substituting for Hi and Hr, that is Ei upon eta 1 plus Er upon eta 2, that is equal to Et upon, sorry, this is eta 1, that is eta 2. So, this is your one equation, and then I have for the electric field, which is Ei cos theta I minus Er cos theta I, that is equal to Et cos theta t. So, second equation I have is Ei cos theta I minus Er cos theta I, that is equal to Et cos theta t. That is your second equation. And again by solving these two equations, we can get a ratio of Er by Ei, which is the reflection coefficient, and Et by Ei, which is the transmission coefficient. So, from here if I do that, I get for the parallel polarization the reflection coefficient which is gamma, and since we are talking about parallel polarization, this is gamma parallel, that will be equal to eta 1 cos theta I minus eta 2 cos theta t divided by eta 1 cos theta I plus eta 2 cos theta t, and the transmission coefficient tau parallel, that will be equal to 2 times eta 2 cos theta I divided by eta 1 cos theta I plus eta 2 cos theta t. So, the expression which you get for reflection coefficient is similar in the two cases, except that this eta 1 and eta 2 are interchange. So, in the perpendicular case we have eta 2 cos theta I and eta 1 cos theta t, whereas for parallel we have eta 1 cos theta I and eta 2 cos theta t. Also note here that in this parallel case 1 plus gamma is not equal to tau, because we have from this equation the relation will be 1 plus gamma, if you take eta 1 on the other side, will be eta 1 upon eta 2 into tau. So, for this case we have 1 plus gamma parallel, that will be eta 1 upon eta 2 into tau parallel. But otherwise all the discussion or arguments we had for the parallel polarization will be identical to the perpendicular case also. So, we have already seen in detail the case of perpendicular polarization. So, all those arguments that the reflection coefficient magnitude will be always less than 1, whereas transmission coefficient could be greater than or less than 1. All those arguments are valid for this polarization also. So, once we have now the reflection and transmission coefficient for these two cases, then now we can combine the reflected and transmitted fields, and then we got the resultant field for the reflected or transmitted wave for any arbitrary polarization. So, let me just summarize and what we have done. We say if you have any arbitrary polarization of the wave, as we have seen, an arbitrary state of polarization can be represented by a combination of two orthogonal polarization, and in this case we are taking two orthogonal polarization which are linear. One is perpendicular to plane of incidence, other one is parallel to the plane of incidence. Solve the problem separately for these two states of polarization. That means you find out the reflection and transmission coefficients for these two cases, and we get the quantities what is called the gamma perpendicular and tau perpendicular, and the gamma parallel and tau parallel, and then you combine the reflected and the transmitted fields for these two polarization to get the resultant electric field, that means the resultant polarization. So, this we will discuss little later how the polarization might get changed, but by using this expression now we can find out how much field is induced in the second medium when the uniform plane wave is incident on a dielectric boundary, and then from there we can also calculate how much power gets transferred to the second medium and how much power is reflected from medium. Now, one of the special cases of this would be that if I take a perpendicular polarization case, this case, and if I make this angle 0, we got the special case which will be the normal incidence case. So, one way is that okay, you start with a normal incidence, then the reflected wave also will be normal because these two angles will be equal. By Snell's law, again this wave also will be moving along the normal. So, essentially we have a case wave moves in this direction, the wave travels back in this direction which is reflected wave, and the transmitted wave also moves in this direction, satisfy the boundary conditions, and you can get a reflection and transmission coefficient for that case. Other possibilities, since we have considered these cases of perpendicular or parallel polarization, either of the case, if I put theta I equal to 0, then I get the case of the normal incidence. So, what we can do, the normal incidence case, and the polarization which we take, whether parallel or perpendicular does not matter, because when this angle becomes equal to 0, the electric field will be either this or lying in the plane of the paper, but they will be perpendicular to this direction. So, I can change, I can take either perpendicular polarization or parallel polarization, I must get the same result. So, let us take, we take the expression which we got for the perpendicular polarization, and from there if we substitute for theta I equal to 0, in this we get from this expression, if I put theta I equal to 0, so theta t also will be 0. So, for normal incidence we have theta I is equal to theta t is equal to 0, and then the reflection coefficient gamma, as we see that this should be same whether it is parallel or perpendicular. So, we just simply say is the reflection coefficient gamma for this, that will be equal to your eta 2 minus eta 1 divided by eta 2 plus eta 1, and tau will be 2 times eta 2 divided by eta 2 plus eta 1. So, that will give me eta 2 minus eta 1 divided by eta 2 plus eta 1, and transmission coefficient that is tau will be equal to 2 times eta 2 divided by eta 2 plus eta 1. And the case of normal incidence is, this is your dielectric interface, this is your incident wave, this is the reflected wave, and this is the transmitted wave. So, this is incident, this is reflected, and this is transmitted. So, this case now essentially has become like a one dimensional propagation. The electric and magnetic fields, the wave fronts are like that. So, amplitude of electric and magnetic fields are not varying in this plane anymore. It has only variation which is in z direction. So, the fields for this would simply correspond to one dimensional propagation in z direction. That means, this case is very identical to the transmission line case, which was one dimensional case. The waves used to travel along the transmission line, and we are not worried about what is the variation of the fields perpendicular to the transmission line. Precisely same thing we are talking about here, that perpendicular to the direction in which this wave is traveling, there is no field variation, and the problem essentially is a one dimensional problem which is identical to the transmission line problem. If I say this medium which is semi infinite and which is characterized by an impedance eta 1, this medium which is again semi infinite. So, if I see in this direction, I will see an impedance, this is characteristic impedance which is eta 2. So, if I look rightwards beyond the boundary, I see an infinite medium ahead, and therefore, the impedance seen will be equal to the intrinsic impedance which is eta 2. If I see in this direction, again I see infinite medium, and I see an impedance which is equal to the intrinsic impedance of the medium which is eta 1. So, that means this case is similar to as if I had two transmission lines of characteristic impedance eta 1 and eta 2, and when the wave is incident from here, this is equivalent to that you have a line which is terminated in an impedance which is eta 2, because this is the infinite medium. So, you see the impedance equal to characteristic impedance. You get the reflection coefficient on this line which is eta 2 minus eta 1 divided by eta 2 plus eta 1. That is what essentially this quantity. So, the normal incidence case, which is the spatial case for any oblique incidence at the dielectric interface, is an identical case to the transmission line. So, when you are dealing with the transmission line, in fact, we were handling one of the spatial cases of this reflection and refraction at the interface. Also, there, since the transmission line was terminated at this point beyond the load, the line was not existing, the power was getting lost into this impedance which was located at this location. But now, when we are having a media like this, then either we can say that the power, this is equivalent to having an impedance at the interface, the power is lost there, but the power is actually not lost at that location, the power has actually gone into the second medium. So, equivalently I can say this is like a transmission line, but the transmission coefficient in this case which says the power which has gone into beyond this point, which was beyond the load point, which was not there on transmission line, but the two are equivalent. So, if I calculate what is the power loss at this boundary, this will be exactly same as what I would have got a power loss into the impedance which is terminating the transmission line. So, this case, the normal incidence case, is the one of the spatial situations of the oblique incidence, and then one can find out the reflection and the transmission coefficient for this. A quick look at, as I mentioned, if I take two polarization either parallel or perpendicular, I must get the same reflection coefficient, but if I go here, which is for the parallel polarization, and if I substitute theta I equal to 0 and theta t equal to 0, I will get a reflection coefficient gamma parallel which is eta 1 minus eta 2 upon eta 1 plus eta 2. One would then wonder, if I said by when theta I goes to 0, two cases should become identical, why the reflection coefficients are opposite of each other? Here is eta 2 minus eta 1, this is eta 1 minus eta 2, and the reason for this is the convention which we have taken for the electric field when we define the direction for the electric field. For perpendicular case, these two electric field were in the same direction, we had taken plus y oriented. So we had a reflection coefficient which is eta 2 minus eta 1. Whereas if we go to parallel polarization, the electric fields are in this direction, so when theta I goes to 0, the EI and ER, they are in opposite direction now. So basically the sign, the negative sign which appears in the expression for when you use for parallel polarization is due to the fact that we have already taken the electric field which is oriented in the opposite direction when theta I goes to 0. So the negative sign essentially accounts for it. What that then means is that when you are having a normal incidence, the reflection coefficient in general essentially can be written like that, with the assumption that initial electric field are oriented in the same direction. So if eta 1 is greater than eta 2, you will have a phase reversal in the reflected field compared to the incident field, and if eta 2 is greater than eta 1, then there will not be any phase reversal of the reflected wave when the wave is incident on a dielectric boundary. So what we see is something important here now, that independent of what are the medium parameters and the angle of incidence, the reflection and transmission coefficient are all real quantities. That means there could be direction reversal for the electric and magnetic fields, but there is no arbitrary phase change either in the transmitted wave or in the reflected wave. These cases are the simple reflection and refraction cases. When we meet next time, we will consider the special case where there is a possibility of getting a phase change which is not 0 or pi, and that will be one of the special cases of these oblique incidences. So we will continue with this, and we will discuss the oblique incidence case in the next lecture, where there could be a possibility of arbitrary phase change at the reflection, at the refraction.